Hello. This video presents the MEDINA framework architecture, along with an overview of the components that make up the framework. The training is structured in 5 chapters. First, we present a diagram which depicts the main building blocks of the framework, with all the components. Then, we will show the data model used. Follows the user management description. Most of the training is devoted to listing and briefly describing the individual components. Finally, some additional information and links where you can find further reading about MEDINA project. Before to start with the overview of the architecture, let us remind the main goal of MEDINA project. To provide a framework of tools and techniques supporting the continuous audit-based certification of cloud services in the EUCS standard. The architecture proposed by MEDINA is shown in this diagram. The diagram can be further divided in 8 building blocks. Each building block corresponds to a well-differentiated functionality of the proposed framework. The first building block relates to the set of catalogs being required by the different roles and personas interacting with MEDINA, and comprise the elements of a controls framework like EUCS. We call it Catalogue of Controls and Security Schemes. It also includes things like technical and organizational measures, TOMs, reference implementations, and equivalences among controls in different schemas. The second block implements the natural language processing techniques proposed by MEDINA to guarantee that new requirements from EUCS or other security schemes are related to the metrics in the catalog. This block leverages a novel ontology to guarantee that requirements, written in natural language, are automatically associated to CSP-specific resources. Our goal is to automatize the current manual process performed by compliance managers and auditors to interpret, map, implement, and assess requirements in their organizations. The risk assessment functionalities provided by MEDINA, both static and dynamic, form the third building block of the architecture. Those functionalities take as input the catalog of controls and metrics, and based on the CSP's risk appetite and assessment results, can control the certification life cycle. The fourth building block comprises the components that manage the life cycle of the certification, which depends on the rules established by the EUCS scheme. National certification bodies, or even pan-European entities like ENISA, can benefit from by becoming public registers of issued certificates. A state of practice challenge for providing automation of auditing or certification relates to the processing of organizational measures, where related documentation of the CSP, e.g. security concepts, operation manuals, is assessed for conformance with the certification scheme's requirements. Building Block 5 implements both a repository for those organizational evidences and the NLP-based techniques for their processing. Complementary to this functionality in MEDINA is Building Block 7, which provides the evidence collection and security assessment of measures by integrating a variety of tools that includes native CSP functionalities. All assessment results, either from organizational or technical measures, are holistically stored and processed in Building Block 6. An orchestrator, in charge of managing the collected evidences and assessment results, and a DLT-enabled evidence manager that guarantees tamper-proof storage of evidences, are core components of this building block. DLT here stands for Distributed Ledger Technology. Finally, Building Block 8 provides the MEDINA integrated user interface to enable human interaction with the rest of components. In this block, we locate also the Corporate Compliance Manager, which is an independent user interface developed for a specific company, in our case, Fabersoft, that communicates with MEDINA tools via API, and where a user can, for example, review the evidence used to issue a certificate or visualize the near real-time status of certificates, Main users of MEDINA framework are also represented in the diagram. They are, namely, the external cloud service provider, internal users of the company, as the control owner and the compliance manager, the conformity assessment body, or CAB, the auditor, and the customer of the cloud services. Now, let us take a look at the data model used in MEDINA. The data model tries to identify the different entities that are used by the components of MEDINA framework and specify their attributes. This figure shows the data model used in MEDINA as an entity relation diagram. As an example, let's have a look to the entity TOM, acronym of Technical and Organizational Measure, that, in MEDINA, is the equivalent of a security requirement. A TOM is represented by his code, name, description, assurance level, that can be basic, substantial or high, and the type. The TOM is always part of a control and can include a reference TOM, which is the implementation guideline for the requirement. Furthermore, the model shows that a TOM is associated, in the one hand, with the entity's security metric, security obligation, and evaluation result. On the other hand, we see that it is linked to 3 questionnaire-related entities. In the MEDINA diagram, entities are categorized into different groups, with the color indicating the architecture building block they belong to. Hence, blue entities are the ones used by the catalog of controls and metrics. They represent the elements in EUCS schema, like framework, controls, requirements, etc., as well as metrics and all those around the questionnaires. Gray entities, like threat and risk, are the ones specifically defined for the risk assessment and optimization framework. Light orange entities are those related to evidence gathering, like cloud service provider, cloud service or resource. They are also employed in the MEDINA ontology. Rose-colored entities are those directly associated to evidence assessment tools. In this case, security obligation and metric implementation. The green entities, that is, evidence and security assessment result, were mainly defined for the use by the evidence gathering and assessment components. Purple entities are those needed to implement the trustworthiness of evidence and assessment results. And finally, the dark orange entities correspond to the cloud security certification functionality. They include the certificate entity, the target of evaluation or the SSI credential, among others. We will now briefly describe the user management in MEDINA, how the users, roles, the authentication and authorization is managed. First thing to say is that Keycloak is used as the identity provider in MEDINA. Keycloak is an open-source identity and access management tool. Users and roles are defined and managed in Keycloak. The use of OpenID authentication protocol allows to every component in MEDINA a standard way to communicate with Keycloak and implement a decentralized authentication. The user-related properties obtained from the user token are then used in the components for authorization, that is, to restrict the access to the features and resources. Roles are a fundamental piece in defining the working workflows. The roles defined in MEDINA, some shown in the architecture diagram, are presented in this table, along with their access level to the CSP's data. Here, Cloud Service Provider level means access to all cloud services offered by the provider. The roles are IT Security Governance, in charge of the business model and products. Security Analyst, responsible for ensuring that the digital assets are protected. Domain Governance, responsible for product security. Product and Service Owner, the central point of contact for a specific IT product or service. Product Security Engineer, who oversees the build, deploy, and run of a product. Chief Information Security Officer, who the Compliance Manager has to report to. Customer, the only non-authenticated role in MEDINA. And Auditor, who refers to an internal or external auditor or to a national cybersecurity certification authority. In MEDINA, each user, depending on his role, is authorized to perform a specific set of operations, using a specific set of tools. Every tool controls the role of logged user and implements the authorization mechanism. We can represent this authorization with a figure for each role. For example, see the case of the Product Security Engineer. The MEDINA toolset is on the left, and the actions the role is allowed to perform with them are in the central box. These actions are ordered from top to down if they pertain to the same workflow, represented by an arrow. The user can, however, perform other actions independent of the primary workflow. Each tool has been represented in a different color that extends also to the tool features or actions. On the right, with a gray background, are represented the pre-requirements. That is, previous actions that are to be performed by other roles. The same applies for the IT Security Governance. The Product and Service Owner. The Security Analyst. The Auditor. Or the Customer, the only non-authenticated role in MEDINA that can only access to the certificates. Now that we have introduced the basics of MEDINA, let us talk about the components of the MEDINA framework. Catalog of controls and metrics. The catalog is the component that stores the EUCS certification scheme. It stores the metrics defined in MEDINA as well. Defines implementation guidelines for the 34 requirements. Provides a mapping of controls in other security schemes. And self-assessment questionnaires for CSPs. It offers a GUI that allows the user to navigate the standard. And an API for the rest of MEDINA components to access the scheme information. This diagram shows the catalog fitting in MEDINA architecture. The input comes mainly from the preloaded data, the EUCS, metrics and questionnaires, and also from an operator answering the EUCS compliance questionnaire. The output is used by a user to consult the EUCS and by several other components that work with metrics. More specifically, the questionnaire results are used by the CSP or the auditor to check the compliance, and by RAOF component to perform risk computation. These tables collect the interfaces and interaction information of the component. For more information about the catalog, check the documentation in Zenodo, user manual and deliverables, the source code in the MEDINA GitLab, and the training video in YouTube. NL2CNL Translator. The natural language to controlled natural language translator goal is to transform a requirement into obligations, expressing them in CNL as a REO object. The main innovation is the use of a metric recommender, based on NLP techniques, to automatically associate metrics to a requirement. This diagram shows how the NL2CNL translator fits in MEDINA. The input data comes from the catalog, requirements and metrics, and from the orchestrator, to obtain the link to the cloud service to be evaluated. The output are REO objects that are sent to CNL Editor for modifying obligation information. This diagram shows how the NL2CNL Translator fits in MEDINA. The input data comes from the catalog, requirements and metrics, and from the orchestrator, to obtain the link to the cloud service to be evaluated. The output are REO objects that are sent to CNL Editor for modifying obligation information. Here you have the interfaces information in more detail. For more information about the NL2CNL Translator, check the documentation in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. CNL Editor. CNL Editor is the component which allows to view and edit the requirement and obligations, REO, defined for cloud services. A user can modify a REO by deleting obligations, changing the operator, or updating the target value to customize it for a specific cloud service provider. It uses a vocabulary based in an obligations ontology and provides a web user interface. This diagram shows the CNL editor fitting in the MEDINA architecture. The input data are REO objects in the form of XML files that come from the NL2CNL translator. Also, the CNL vocabulary, which is based in the catalog metrics, is used as input. The output, on the other side, are the REO objects updated that are sent to the DSL mapper. The user can not only edit but also delete REO objects. These tables summarize the interfaces and interaction information of the CNL editor. For more information about the CNL editor, check the user manual and deliverables in Zenodo, the source code in the MEDINA GitLab repo, and the training video in YouTube. DSL Mapper. The DSL Mapper maps the obligations expressed in CNL into executable policies expressed in domain-specific language. In particular, the DSL chosen in MEDINA is the REGO language. REGO code is used by the MEDINA evidence management tools to automatically evaluate these policies to verify compliance with a certification scheme. In this diagram, you can view how the DSL mapper fits in MEDINA architecture. Its input data comes from CNL Editor and the MEDINA ontology. The output is a set of REGO rules, one for each obligation, that will be used by Orchestrator to assess obligations. Here you have the DSL mapper's interaction summary. For more information about the DSL mapper, check the documentation in Zenodo, the source code available in the MEDINA GitLab repo, and the training video in YouTube. AMOE-Assessment and Management of Organizational Evidence. AMOE examines the company's policy documents, extracting from them evidences to compute hints or metrics pre-assessments. The user is who finally decides the assessment result that is then forwarded to the orchestrator. See here the AMOE tool into the MEDINA architecture diagram. AMOE input consists in the document from the repository, and metrics data and configuration extracted from the catalog and the orchestrator, respectively. The output data, consisting in evidence plus assessment results, is sent back to the orchestrator. The user interface allows you to upload documents and set and submit assessment results. The information of AMOE we just described is gathered in these two tables. For more information about AMOE, check the documentation in Zenodo, the source code available in the MEDINA GitLab repo, and the training video in YouTube. Cloud Evidence Collector. The Cloud Evidence Collector is the component that collects data from cloud resources, e.g. Azure, AWS, Google Cloud, or others, and translates them to MEDINA Evidence's data model. It provides a separate package for each vendor that discovers resources, collects data, creates evidences, and forwards them. This diagram shows the Cloud Evidence Collector fitting in MEDINA. The input consists in the measures taken in the cloud resources. The data is transformed into MEDINA evidences and sent to the Security Assessment tool. In the case the collector besides assess the evidences, then both evidence and assessment result are sent to Orchestrator. Here you have a summary of the interface's information. For more information about the Cloud Evidence Collector, check this documentation in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. Codyze. Codyze is an evidence collection tool that collects data from source code and assesses it to verify if it complies to security requirements according to MEDINA metrics. To do this, first, requirements are broken down into checkable source code properties, and then Codyze verifies the source code and can provide evidence and assessment results if a requirement is sufficiently realized in software. This diagram shows Codyze fitting in MEDINA. The input data is the source code of the applications to be examined. The output are the subsequent assessment results that are sent to the orchestrator. These tables summarize the interface's information of the component. For more information about Codyze, check this documentation in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. Wazuh. Wazuh is an evidence collector dedicated to threat detection in the CSPs. It is supported by agents that are installed on the machines to be monitored, and based in rules that include internal metrics and thresholds to trigger events. It extracts the data relevant for MEDINA metrics and transforms it into evidence. Wazuh controls malware protection, logging, threat analytics and automatic monitoring. This diagram shows Wazuh fitting in MEDINA. The input of Wazuh server consists in the measures taken by the Wazuh agents in the cloud resources. The data is transformed into MEDINA evidences and sent then to the Security Assessment tool. Here you have a summary of the interface's information. For more information about the Wazuh, check the deliverables in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. VAT Vulnerability Assessment Tools. VAT is a vulnerability scanning and detection framework, intended to be deployed in the CSP's infrastructure to periodically scan the machines on the monitored network. VAT uses several tools to detect vulnerabilities as web vulnerabilities, network reconnaissance, vulnerable software, and other specific vulnerabilities based on custom scripts. This diagram shows VAT fitting in MEDINA. The input of VAT server consists in the measures taken by the VAT agents in the cloud resources. The data relevant for MEDINA metrics is extracted, transformed into MEDINA evidences, and sent then to the Security Assessment tool. These tables summarize the interface's information of the component. For more information about VAT, check these deliverables in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. Security Assessment. Security Assessment tool is responsible for evaluating incoming evidence. Evidence is received from the evidence collectors, such as Wazuh, VAT Evidence Collector, etc. Then a policy written in Rego language asserts that an input evidence conforms to user-specified constraints, like target values and operators. Both input and the policy written in Rego are aligned with the cloud resource ontology. This diagram shows security assessment fitting in MEDINA. See how the input data comes from different evidence collectors. The data is then transformed in MEDINA assessment results, and the outcome is sent to the orchestrator, and will eventually reach the continuous certification evaluation component. These tables collect the interfaces and interaction information of the component. For more information about the security assessment, check the documentation in Zenodo, the source code in the MEDINA GitLab repository, and the training video in YouTube. Orchestrator. The orchestrator is the central component of the MEDINA framework, which processes evidence and assessment results, receives data from the security assessment tools, stores evidence, assessment results and other related data, and forwards assessment data to other components. Is in the orchestrator where the user creates and configures new cloud services and targets of evaluation. Also, one can consult there the status of certificates issued to cloud services. This diagram shows orchestrator fitting in MEDINA. Inputs are the metrics from Catalogue, Rego rules from DSL Mapper, assessment results from assessment tools, and certificate information from Lifecycle Manager. The outputs are assessment results that are simply forwarded to CCE and RAOF, and transformed to hashes and sent to the Trustworthiness System. Here you have the interfaces information in more detail. For more information about the orchestrator, check the user manual and other deliverables in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. Trustworthiness System. Trustworthiness System provides a secure mechanism to maintain an audit trail of evidence and assessment results. The proof of integrity is based in smart contracts in blockchain. It provides long-term records and a GUI to access the MEDINA's audited information. This diagram shows trustworthiness system fitting in MEDINA. The input data, evidences and assessment results comes from the orchestrator. There is no output to other components from the trustworthiness system. An auditor can check the information saved on the blockchain either manually via GUI or automatically via API. These tables collect the interfaces and interaction information of the component. For more information about the trustworthiness system, check the user manual and other documents in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. CCE, Continuous Certification Evaluation. The CCE collects assessment results and evaluates the compliance on all levels of the certification hierarchy, resources, requirements, controls, control groups, and standard. For this, it aggregates the values for each metric and builds an evaluation tree representing the result of the assessment on higher levels of the certification scheme. This diagram shows CCE fitting in MEDINA. The input data are the evidence that come from the orchestrator and the metrics data from the catalog. The output is the evaluation tree that can be graphically consulted by the user in the GUI, and which is sent to the RAOF for risk assessment and to Lifecycle Manager for the certification decision. Here you have a summary of the interface's information. For more information about the CCE, check the user manual and other deliverables in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. RAOF, Risk Assessment and Optimization Framework. The RAOF implements a service for a quick and simple risk assessment, which is used as a background for the assessment of nonconformity of CSPs. It supports both manual analysis by a compliance manager using the SATRA GUI and automatic analysis during the continuous monitoring phase, when the tool periodically receives the evaluation results and performs the assessment. Also, it provides optimization of the effort for ensuring the compliance. This diagram shows RAOF-in MEDINA. The continuous certification evaluation component collects and sends all the evidences to the RAOF. The RAOF conducts the risk-based nonconformity assessment, whose result is sent to the Certificate Lifecycle Manager, where the decision about the state of the certificate is made. Another input connection is with the catalog, which send the user answers of the questionnaire. These tables collect the interfaces and interaction information of the component. For more information about the RAOF, check the user manual and other deliverables in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. Lifecycle Manager. Lifecycle Manager goal is to aggregate relevant data for the certification decision and automatically derive a preliminary certificate state. The decision is based in the risk assessment deviation received from RAOF and the operational effectiveness received from CCE. The certificate states are defined according to EUCS schema, new, suspended, withdrawn, etc. This diagram shows Lifecycle Manager fitting in MEDINA. The input data is the risk assessment, e.g. major deviation, coming from the RAOF, and the operational effectiveness, coming from the CCE. The output is stored in the Orchestrator database and forwarded to the SSI system. Here you have the interfaces information in more detail. For more information about the Lifecycle Manager, check the deliverables in Zenodo, the source code in the MEDINA GitLab, and the training video in YouTube. SSI, Self-Sovereign Identity Framework. SSI provides CSPs the capability to manage their own identity through verifiable credentials. Allows the CAB to issue, update, and revoke security certifications. Allows the CSPs to store verifiable credentials about the certification status identity in their own user space. And permits the client to verify the credentials. This diagram shows SSI fitting in MEDINA. The Certificate Lifecycle Manager sends the input data which, with the contribution of the certification authority, is transformed into verifiable credentials and proofs. The SSI doesn't provide any output to other components. Instead, an auditor, a customer, or a CSP employee can check the information on certificates through the user interface. These tables summarize the interface's information of the component. For more information about the SSI, check the user manual and deliverables in Zenodo, and the training video in YouTube. IUI, Integrated User Interface. The IUI is the component that encapsulates the graphical user interfaces of all MEDINA components. Based in micro front-end web architecture, is the landing page of the MEDINA framework. Integrates all the tools providing a common look and feel, and interacts with Keycloak for the authentication and authorization. This diagram shows the IUI fitting in MEDINA, a web-based tool that integrates all the components' user interfaces. In a unique user interface, that is the only entry point for the users of MEDINA framework. Here you have the interface's information in more detail. For more information about the integrated UI, check the documents in Zenodo and the training video in YouTube. CCD-Company Compliance Dashboard. The Company Compliance Dashboard, or CCD, is the equivalent of the IUI, but based in an already existing tool that connects to the MEDINA core APIs. It manages all the cloud certification processes and uses the Fabersoft Cloud UI and Highcharts functionalities. The CCD demonstrates the modularity of the MEDINA framework, which customers can integrate seamlessly into their own ecosystem. This diagram shows CCD fitting in MEDINA. Take into account that, although we have represented both CCD and the integrated UI in the same box, they are two different tools with an equivalent function. Here you have a summary of the interface's information. For more information about the CCD, check the documentation in Zenodo and the training video in YouTube. Now that we have presented all the components of the MEDINA framework, let us finish by citing some sources of further information available to early adopters. If you need more details about the components presented so far, or about the MEDINA project in general, you can visit the official web page on the first link, where you will also find all public deliverables of the project. Project-related videos, such as demos or training videos, are available in the MEDINA YouTube channel. If you want to explore in more detail the components of the MEDINA framework, be sure to check them out. The third link points to the MEDINA community in Zenodo, where, among other things, the papers produced during the project are available. Finally, the source code of the project is available at the last link in the MEDINA GitLab. And this is all regarding the MEDINA architecture. Thank you for your attention, and goodbye.